Good evening. You guys should have just finished your bell ringer and finished reviewing your bell ringer. If you guys haven't done that yet, just pause me and y'all quickly work through that and correct in a different color ink and send those in so I can give you guys some daily points for those. Here's what we've got on tap for today. We've got to work through homework. I know that there were some issues in that related to, I'm assuming, the oxidation state ones. I wasn't real clear on exactly what it was, but I'm going to work through those. I've looked at them. They don't seem too out there, so I'm just going to assume I didn't do a very good job explaining the other day, and that's what's causing that. So we're going to work through those. I'm going to go quickly back over redox, oxidation and reduction, what that is and what that means. And then we're going to introduce stochiometry, what that is, work some problems with that. And then I'm going to send you guys a couple of YouTube links for you guys to watch through if you're still confused on any of these topics, and then tell you what you need to study for your quiz that we have on Tuesday. All right, so without further ado, let's work through some of these oxidation and reduction questions. Okay, first we're going to start with the oxidation state questions, which was number 8, and then we'll quickly do 9 and 10 was we're just going to reactions 1 through 7. Okay. Okay, well, we'll talk through those. All right, so first, let's talk through a lot of these. And in one of these links, he actually does a really good job explaining the rules. And he said something that made me feel a little bit better, because these oxidation state rules were not the ones that I learned in college or high school chemistry or whatever. And he said that there's pretty good variation in how people list those. And so I want you to look at these, and they agree with what he says. He has them in a little bit different order, and they're actually a little bit clearer the way he says them. So I'm going to encourage you guys to watch through that. He's an excellent explainer, the Tyler DeWitt guy. But I'll have those links for you guys in an email or in handouts or some way for you guys to have those. All right, so let's go through these rules for determining what the oxidation states are, and kind of try to get them where there is a unified concept behind them rather than just a bunch of kind of random rules. All right, so let me get us a little bit closer here so we can maybe get a little bit better view of this. Okay, all right, so what are our rules here? Crooked there. All right. Atoms alone or bonded with themselves have an oxidation state of 0. Okay, and remember that's because, first of all, if he's by himself, we assume that atoms are in a neutral state, unless we have some reason to believe that they're not. Okay, so they should have an oxidation state of 0, because remember, oxidation state's got to do with whether the electrons are being added or taken away. Okay, from that neutral state. So if they're in that neutral state, it should be 0. Also, since it's related to electronegativity, if it's bonded to itself, in theory, those electrons should be perfectly balanced. And so if something's bonded with itself, there's no difference in electronegativity, there's no difference in sort of share of the electrons, so that should also be 0 as well. And then, I just wrote this one. It's not just diatomic. It's whenever that's just that pure element. So he lists P4 and S8, sulfur 8, Cl2, H2, N2, O2, all those. And any pure element has 0. Okay, so those are the zeros. Okay, all right. Fluorine, because it's our most electronegative, is always -1. Okay, he's always going to be the first one you look to if there's of fluorine to set the numbers. Oxygen is almost always a -2, except in peroxides where it's a -1. Okay, and he mentions in his video, so I'll mention it here as well, that H2O2, as in hydrogen peroxide, the stuff you put on a cut and it fizzes, it's a peroxide, and he says it's probably the only peroxide you'll see. That's certainly the only one I'm ever going to ask you about. But in this one, we know that oxygen is a -1. Okay, we're not going to get any deeper into the why of that or what's special about that electron arrangement that lets it be that way. That is what it is. Okay, it's a -1. All right, and so you just got to get familiar with these. Okay, so generally speaking, these are 0. Fluorine's always a -1, no exceptions. No exceptions, no exceptions. Oxygen's almost always a -2 with this single exception of a peroxide. Okay, all right. Halogen should have oxidation number or oxidation state of halogens is -1 unless they bond with oxygen. Well, why is that? Because oxygen is more electronegative than most of the halogens, except for fluorine. Okay, if we look back at our electronegativity stuff here, that's what determines how we figure out whose number we look at first. Okay, so if we just look at the electronegativities, we've got a 3.98. He's setting the trend. He's always going to be a -1, no exceptions. Nobody's more electronegative than fluorine. Then after that, oxygen sets the oxidation states in a compound because he's the most electronegative, unless fluorine's involved, because he's more electronegative. Okay, so it's just the electronegativity of them, generally speaking, that sets their number. All right, and like we said in peroxides, that oxygen is sort of choosing to be a -1 because of various things. Okay, something is not forcing it to be. All right, so good. We now know the order that we need to look in: fluorine, and then look for an oxygen. All right, and then we look at the halogens, and they're generally a -1. Hydrogen, then, this H, is a -1 with metals and a +1 with nonmetals. Okay? And generally, that's because these are more electronegative than hydrogen, generally speaking. And over here, hydrogen's the more electronegative one. Okay? Meaning he wants to pull electrons towards himself, meaning he likes to have a negative oxidation state. Okay? And everything must add up to 0 or to the charge on the polyatomic ion. Okay, we'll get there and we'll reinforce all of these here in just a second. Okay? And as Tyler says in his video, and I'll mention, our book doesn't even really clearly state it, but typically these are +1 and these are +2. Okay? Typically. Unless something is telling you, like if he's bonding with fluorine and it makes his oxidation state something else, then the fluorine dominates on that. All right, so let's roll through these and see what applies and what doesn't. All right, I did this first one here. All right, we got a Br and P. So we've got phosphorus, bromide. Okay, how do we approach this? All right, well, we don't say anything about phosphorus. Okay, as far as like a rule. Okay, so he could kind of go one way or the other. Could be a +3, could be a +2, could be a +1. Who knows, right? We don't have a rule for it, so we don't look to him first. We'll look at bromine. Okay, bromine is right there in the halogens, and you guys can be flipping back and forth. I'm not going to try and keep showing my periodic table because it gets hard to do with this camera. But this is a halogen, so we're going to go ahead and set that as a -1. Okay, there's 3 of them, so that becomes a -3 total. They must add up to 0. This is not an ion with a charge, so that means P has got to be an oxidation state of +3. Okay, so we should have P 3+, Br 1-. Okay, and I don't have any particular way we need to write that or anything, so I'm just doing that for clarity here. All right. Yes. 2O5. All right, so let's look. So we have arsenic there. Don't have a rule about arsenic. Do have a rule about oxygen. What's that rule? -2 except in a peroxide. This is not a peroxide situation. All right, so we're going to assume that it's -2. All right, and obviously that gives a -10 here. So there are 2 here that have got to make up a +10, so this is a +5. Okay, so it's +5, and all right, next, ClO4 minus. Okay, so now we've got a polyatomic ion here. Okay, so what happens? All right, halogens are -1 unless they bond with oxygen, and oxygen dominates. Okay, so we know that this is going to be a -2 for a total of -8. So what's this got to be? Well, they've got to add up to be a -1 right here. So this has got to be a +7. Okay, so we have chlorine 7+, and oxygen is a 2-. Okay, how does he like for you guys to write these? I don't have a particular opinion, but I want us to all kind of be doing the same thing. Okay, he just wants you to write it like he'd be fine writing it. He actually writes his okay. It's clear to me that you know what the oxidation states are. I don't really care. You can write it like this. You can write it just in kind of like a matter of fact, all in the same font, no superscript or subscript. That's fine. Okay, make it clear. Don't make it look like a subscript, but just make it clear that you know what you're talking about, right? F2, what's the rule that dominates there? Is it -1? No, because atoms alone or bonded to themselves have 0. So F is 0 here. Okay? All right. So you just got to find the rule that applies. All right. So UF6. Okay. And interestingly, this is actually the compound that they enrich uranium. This is a gas right here, and they enrich uranium with the different isotopes of uranium using UF6 here. So that's a real deal. All right. So we don't have any rule about U. It's just a transition. It's not a transition metal. It's an actinide metal there down below the periodic table. We don't have a rule about it, so it can change its oxidation state. Fluorine, always -1. All right, so what's that give us? -6. So U's got to be +6. Okay. CO3, 2-. Okay. What do we have? We don't have a rule about carbon. Carbon can take multiple oxidation states. Okay. And when I say it can take multiple oxidation states, that just means we don't have a rule for it. Okay. It means it does whatever it needs to do to make those charges work out the way they do. Okay. So this is going to be a -2 for each of these oxygens times 3 is going to give us a -6 total. It's got to add up to a 2-, so that makes carbon a +4. So carbon is a +4 and oxygen is a -2. Okay. When you're writing this, make sure it's clear to me that you are showing me that the oxygen, individual oxygen, is a -2. Okay. All right. Keeping on going. H3PO4. Okay. All right. So what do we know here? Okay. We don't have a rule about him. Okay. We don't have a rule about phosphorus. So let's do the rules that we do No. Okay. Oxygen, so -2. What's the rule about this hydrogen? It could be a +1 or a -1. Is it with metals? Nope. P, O, those are both nonmetals, so it's got to be a +1 as well. I say as well. We have a rule for it, so we know that it is a 1 plus. Okay, so what does that mean? We've got a +3 from the hydrogens. We got a -8, -2 times 4. And what does that leave? This is a -5, so he's got to be +5. So we would want to say that hydrogen is a +1, phosphorus is a +5, and oxygen is a -2. Okay? I hope these are getting a little easier to understand what's going on, what the rationale behind them is, okay, and what the order that you apply those rules in. Okay, so what do we got? We got zinc, nitrate. All right. So what do we have here? We know that this is going to be a -2. All right, and then we know that this. All right, how are we going to approach this? We got a couple unknowns here because we don't have rules for nitrogen or zinc. Okay, so what our approach needs to be is we look back and see what this polyatomic ion takes as a whole. Okay, we look back at our polyatomic ions very quickly. I'm going to find where that is. NO3 takes a 1-. Okay, so what do we have? We've got -2. We've got 3 of those, so that's a -6. We want this to be a 1- overall, so that's got to be a +5. And then we've got 2 minuses here, so this has got to be a +2. So you guys would have been able to do this if I hadn't been asking you about individual oxidation states, because you would have memorized that an NO3 is always a 1-. Okay, and then there's 2 of those, so this has got to be a 2+. Okay, so you got to sort of have cumulative knowledge here in which we've covered some of this stuff, and we're trying to get it all to hang together here and apply everything that we've learned from all the past chapters to get that together. Okay, I'm not going to ask you that on a quiz. Okay, we're doing this so we can discuss it in the homework, but I'm not going to ask you to have memorized all the oxidation states of all the things and always have those memorized. Okay, we're not doing that. All right. So anyway, so we have to sort of logically work our way into it, in that we know what oxygen is, we know what the polyatomic ion is, and then we know what has to happen for that to be 0 overall. Okay, so we end up with zinc as a +2, nitrogen +5, and oxygen is a -2. Okay. All right. Keep on rolling. We're getting closer here. Let's come up here. All right. So C4H10. Very straightforward. Is it with a metal? Nope. It's with a non-metal, so it's a +1. So we've got a +1, and what does that give us? A +10. Okay. And then what does that mean here? It means we've got to have 4 of those. A -2.5, which is not normal. So let me see what he has there. Hey, he has a minus 2.5. It's interesting. We don't normally see decimals in the oxidation states, but that's acceptable. So again, the rules are the hydrogen is bonded with a non-metal, and so we know what its oxidation state is, and then this has got to overall be 0, and so we just divided up the 4 of those. So C negative 2.5 and H plus 1. Okay, very quickly now, Cr2O7, and that's got to be a 2 minus overall. So what do we have? We've got a negative 2 here because we don't have any rules about chromium. Okay, so that's going to be end up being a total of negative 14. And so what does that mean here? It means these have got to be plus 7. Okay. Oh, wrong. Sorry. This is negative 14, but we're 2 minus overall. So that means we only need to make up 12, which needs this one to be a plus 6. Okay, so we have chromium is plus 6 and oxygen minus 2. Okay, that's super bad writing there, minus 2. Okay, KH, pretty straightforward. What is H? It's with a metal, minus 1. That leaves him with a plus 1, which is good because we know that K is in the first group there, and we would expect it to be a plus 1 just from what we know about those oxidation states that we've been talking about since almost the beginning, how they like to lose electrons. All right, and then Fe, no, what is it? It's by itself. It's a pure element there, so it's 0. Okay, and so you should be able to follow your way through those things. All right, 9. Why must chemical equations be balanced? Why must they be balanced? Well, conservation of mass. Okay, those atoms can't go anywhere. They have to be sort of permanently around. They can't just disappear from the equation, even if they're given off as a gas. We have to show that they're given off as a gas, as if they're sort of still hanging around in there, because they can't just disappear. Okay. All right. For the reactions in exercise 1 through 7, let's identify them as what they are. Okay, and very quickly, we remember what are our types. If we synthesize something, that's A plus B goes to AB. The opposite of that is decomposition. AB goes to A and B. Okay, then we have combustion, which we have some hydrocarbon of some type, and that's with some amount of oxygen, and that goes to CO2 and water. All right, and then we have single displacement or replacement. Okay, I've heard it both ways. And that's what? A, B, which is a compound, plus C. That becomes A, C, and B. We talked about this is often related to the activity series of metal. Okay, we'll talk a little bit more about that when we talk about our quiz that we're going to take. And then we have double replacement or displacement. We have AB plus CD goes to AD plus BC. Okay, so these swap places. All right, so very quickly, let's walk through these. And if these are too complicated, that's my fault. I'm just not as familiar with that as I should be. But let's see if we can muddle our way through them here. All right. Butane burns in oxygen to produce carbon dioxide and water. Combustion, period. That's what it is. Okay. Like CXHX, in this case it's C4H10. It burns and produces carbon dioxide. It'll always produce carbon dioxide and water as its products, and it always will be reacting with oxygen. Okay, so that's just, those are the hallmarks of that. All right, iron sulfide reacts with hydrochloric acid to produce hydrogen sulfide and iron chloride. Okay, so let's just write out what it is and not try to do any more than that. We're not trying to balance it, anything like that. All right. Iron 2 sulfide, offhand, we don't even need to know what that really is. I think that's sulfide. Hydrochloric acid, which is just HCl. And I can see how this would be difficult if you were not familiar with these, but these are not unknowable elements or unknowable compounds here. So, all right, and then it goes to hydrogen sulfide. Which I think is that, and iron chloride. Okay, so what's happened? This and this have swapped places. Okay, so that is a double displacement or replacement. Either one is satisfactory to me. Okay. 3, it tells you it's combustion. 4, carbon monoxide and hydrogen become CHOH. Okay. Well, what's going on there? Okay. This is not, excuse me, CH3OH. This is not as clear cut, but this is a synthesis reaction. We've got smaller molecules that are combining to make a larger molecule. Okay, so that's a synthesis reaction. Okay, and of course there are all sorts of different types here, and again, as you study chemistry later in your life, you'll see that there's more complexity to this, but you know, you're really only picking from these 5 for right now. Okay, and we've also got acid neutralization. Okay, so acid plus base is equal to goes to a salt plus water. Okay, so it's going to be one of those, and so don't make it more complicated than it is. If it's smaller things making a bigger thing, that's synthesis. All right. Potassium carbonate is used to neutralize the sulfuric acid in well water caused by acid rain. The products of the neutralization are potassium sulfate, carbon dioxide, and water. Okay, I don't love that carbon dioxide there, but it tells you it's a neutralization reaction, so we'll go with that. Okay. Tungsten metal is produced by reacting tungsten oxide. It's tungsten TN, TG. Tungsten. Of course, now I can't find tungsten on here. Ugh, rats, where is it? Okay, well. Ugh, terrible. All right, tungsten oxide. We'll just pretend it's TN. With hydrogen gas to produce tungsten metal and water. All right, so what's going on there? We have, let's see, AB plus C, and that goes to A plus B, C. I'm not actually sure what that's classified as. Let's see what he has to say, because it doesn't really fit our standard formula. These homework things are super not straightforward often, which is strange to me. FES double replacement. It's number 10 here. And okay, I don't even understand his answer. Where is the listing of what's going on there? Butane, it's none. What's he talking about? It's none. It's a combustion. Okay, I don't really understand why the homework is like that. Okay, I'm not sure what this is because this doesn't follow. This is not normally we would see. You know, if this was going to be a single replacement, this would become AC plus B. Oh no, okay, the C is replacing the A. Sorry. Okay, so this is a single replacement. Okay, because that C is coming in and kicking that out of there. That's what was confusing me. That hydrogen's acting like a metal here. Okay, so he's replacing the metal, and then the metal goes free. Okay, so that's a single replacement. One thing is being replaced. All right, and finally, sodium azide, NaN3. Becomes sodium metal and nitrogen gas. Pretty standard decomposition. Okay, and I haven't looked at y'all's homework yet to see what all you have gotten right or wrong on that, but like I said, I'm going to follow up with these YouTube links. He's going to explain a lot of it. Okay, or if you got more questions on that, let me know. I appreciate you guys letting me know in the group me that you weren't understanding. That helps me to know what you guys don't understand. All right, very quickly on the stoichiometry. All right, so stoichiometry is one of those things that's sort of so foundational, it's almost hard to even like talk about it because every time you do anything with any equation, you're doing stoichiometry. Okay, and I'm just going to write what he's got here. And then we're basically just going to jump in and start working some problems here. All right. The purpose of stoichiometry is that we are trying to know if I've got X amount of this thing and X amount of that thing, and this is the chemical equation for what those two things do together, how much of the product is produced. Okay. And sometimes those questions can be asked in moles, sometimes they can be asked in grams, sometimes the information is given in moles, sometimes it's given in grams, okay? And basically stoichiometry is one big conversion problem, okay? And that's why we hammered that so many times, because it just is so foundational to have that skill, okay? All right, so let's look right here. Rule number 1, do everything in moles. Okay. All right, and we'll explain why that is in just a minute. Okay. This is on 187 here if you guys want to look in your book there and see all the other stuff he's got to say. Okay. And the mole ratios come from the coefficients. Okay, the ones we were just writing in front of those balanced equations. Okay, or when we were balancing the equations, those coefficients that we were writing in front of there, that's what those are. Those are mole ratios for how things react together. Okay, and again, it seems like it's so very foundational to how we even think about how, it's one of the things we talked about very early on, one of the main chemical things. What do you say? You know, it's all about modeling, and it's all about whole number ratios of atoms. Okay, this is tied in with that. Okay, when we got water, it's always 2 H's and 1 O. Okay, and similarly, when things react, it's always X H2O. So, like for example, let's look right here. Okay, when photosynthesis goes on, it's always this. It's always 6 CO2s and 6 H2Os produce 1 sugar and 6 diatomic oxygens. Okay, always. And so we know if we have so many of these, it's got to have so many of these to make 1 of these and 6 of those, or it just doesn't even go. It just doesn't make enough of them. Okay. All right. So let's just dive right in and work some of these. Okay. All right. So part of the difficulty, part of the challenge of this is going to be getting from the word problem into the math problem, you know, not just having it given to you as a math problem. Okay, it's always the tough thing. It's always what everybody I work with in math struggles the most with. So that's part of what we've got to overcome, is just getting these word problems into the math problem so we can work them. Because once it's a math problem, it's really not that hard. All right, so what do we have? We're going to just work through right here on page 188. All right, let's determine how many moles of water are produced by the reaction. We have 13.55 moles of O2 with propane. Okay, and propane C3H8. We have unlimited C3H8. Okay. And we know that the equation is this, C3H8, and I'm pulling this from page 186, plus 5O2 goes to 3 CO2 and 4 H2O. Okay? All right, so let's analyze this a little bit more before we get going. Okay, this means that if we have 1 mole of this, so, you know, literally if we had 6.022 times 10 to the 23rd molecules of propane, we would need 5 moles of oxygen to react with that 1 mole to produce 3 moles of CO2 and 4 moles of water. Okay, and I've omitted the states of these for clarity. Okay, so I'm not worried about this being gas, liquid, any of that stuff. Okay, we're focused on these coefficients for right now. All right, so what do? So we know that we've got unlimited this, okay, and this kind of brings up what we're going to talk about next class period, which is limiting reactant, the one that runs out first. Okay, we don't even know how much propane we've got. We're just going to burn propane until we've used up all of our oxygen here. Okay, all right, and so what do we want to know? We want to know how many moles of water. Okay. So how are we gonna do this? All right. So we're gonna treat this like a conversion problem. All right. We're trying to get, in other words, trying to get from 13.55 moles of oxygen, okay, to some number of moles of hydrogen, and our conversion factors are gonna be these coefficients. So what do we have? We got 13.55 moles O2, and you always want to check and make sure this is a diatomic and that it's diatomic in the equation here. Okay, we'll talk about what you do with that in a little bit. Okay, if they're not. All right, so what do we want to do? We want to get from O2 to moles H2O. Okay, so just like conversion before, we want to cancel out what we've got on the top and replace it with something else. All right, so what do we have? So for every 5 moles of O2, what have we got of H2O? We've got 4 moles of H2O. Okay, and what happens? Moles O2, moles O2, we multiply and then divide, and we end up with 10.84 moles of H2O. Oh, surely he's doing just the easy ones, you guys are thinking. There's going to be super hard ones in the homework, and they're going to be really tough, and he's only going to do the easy ones, and we're going to be stumped. All right, well, let's talk about what else can be difficult here. All right, so the other thing that you can be given, what if I'd given you this in, if I said 13.55 grams of O2? Okay, well, you would have had an extra step in which you converted from grams to moles, okay, and then you'd be in the same situation. You have to get the grams to moles, and then you'd be just like you'd given moles here and end up with moles there. All right? If I'd given you grams here and asked you for how many grams of H2O, you go grams to moles, then you're right here. This spits out moles, and you go moles back to grams for H2O. Okay, so the simplest one you can do is moles to moles, because that is a straightforward ratio you're getting from here. If you're given grams and they ask you for moles at the end, you got one step on this side. And if you've got grams and you're going to grams on this side, you got to go grams, moles, moles, grams, and then you're done. Okay, so at best, you've got 2 cells you've got to do, and at worst, you've got 4 you got to do. But the good thing is you guys know how to do all that already, and it's just keeping it straight in your mind what you've got to do. Okay? All right, so let's look. Let's see. Let's go and work an actual homework problem. Maybe. All right, I'm gonna grab one right here. All right, I had to look some of these up, and this is part of what I don't love about some of these homework things here. So we're gonna work 19 here, okay? And I had not worked this beforehand. All right, so what we're going to do is, first of all, I had to look up aluminum hydroxide and aluminum chloride. So you'll look at what 19 is. That's page 197. All right, so you will always be given at least the unbalanced chemical reaction. Okay, I'm not going to ask you guys to know how things bond or what a particular thing is without at least giving you this. All right, so the first thing we got to do is balance. Okay, we don't know the stoichiometric rate relationship like here. This is the balanced one here, and I didn't check that. I assumed it was. This is the one he was using. Okay, so but we can't know that it's balanced if we didn't have any of these coefficients in front of them. So let's check it right here. We got 1 aluminum and 1 aluminum. We got 1 chlorine and 3 chlorines. I'm going to drop a 3 in front of this guy right here. Gives us 3 hydrogens. We got 2 hydrogens. All right. This is, of course, not going to be simple. We got 3 hydrogens and 6 hydrogens here. So let's put a 3 in front of that guy. And does that solve our problem? 1 aluminum, 3 oxygens, 6 hydrogens, 3 chlorine. All right, so now we're balanced. All right, you have to balance it because that's where that mole ratio comes from. Okay? So if you have something, and I just written it like I just wrote that, you've got to check to make sure that it's balanced. All right. And what does he ask us? 750 milligrams of aluminum hydroxide are consumed. Okay. We're looking for, let's just do one of these for the sake of time, the mass of water produced. Okay, how are we going to do this? Okay, so basically what he's saying is, given these conversion factors in this formula, okay, we need to convert 750 milligrams of this into some number of, we could say milligrams, that's fine, of water. Okay, so let's just do that conversion. Okay, we have, I'm just going to draw this separates out. All right, so what do we have? We have 750 milligrams AL. Wait, I can already tell I'm going to be out of space here. Let me. I'll do it down here at the bottom. I think I'll have room if I do it here at the bottom. All right, I've got 750 milligrams of AlOH3. Sorry. Okay. So what's the first thing we've got to do? What did we say we had to do? Okay. We said we have to get into moles first. Okay. So we're going to say 1 mole of AlOH3. Right, and then we go back to the stuff that we learned back last semester. And what do we got? Al, and then 3 O's and 3 H's. So what do we have? We have 27 plus 3 O's is 48 plus 3 H's, and we'll just 3. Okay, and we're just doing the round numbers here. You know, try to do them to 1 or 2 decimal places. Okay, the point of this is not to be super exact and be, you know, we're not in the lab here. We're not trying to get to the microgram here. We're just trying to do the stoichiometry. All right, and so that's 27 plus that, and that's all grams of AlOH3. Okay. All right, and so we need to remember that this is milligrams, and I'm just going to go ahead and make this conversion because I need it to be a little bit clean, and I'm going to be tight on space here. So I'm just going to say not 750 milligrams, but 0.750 grams. Okay, and I would just, if I were you, I would add 1 over there, and I would just say 1,000 milligrams per 1 gram, and arrange them so that they cancel out the units. Okay, so we're now in grams because that's what this comes out of the periodic table in. Okay, so we always want to be careful with our units here. All right, so now we're in moles here. All right, so now for each mole of AlOH3, now we say, well, what are we trying to do? We're trying to get to water. All right, so for each 1 mole of this, we've got 3 moles of that. So now we're going to say 1 mole AlOH3. We're going to have 3 moles of water be produced. Okay? And if they had asked us how many moles of water that produced, we'd be done, but we're not because we're looking for the mass of H2O produced. Okay? So we got to get out of moles. So we're going to say 1 mole of H2O, and what's that? 16 plus that is 18 grams of H2O, and that should be our answer. Okay, so very quickly, let me do this, and that'll be it. All right, so 0.75 times 1 times 3 times 18 is 40.5 over 27 plus 48 plus 3 over 78. And let's make sure everything cancels out. Grams aluminum, moles aluminum hydroxide, moles aluminum hydroxide, moles of water, and we're left with grams of water. So we then just plug that into our calculator, and we get 0.52 grams of H2. And if we wanted to, if it had been specific, we could say 519 milligrams of H2O. Okay? So you can see how this structure of this is very similar to just a conversion. Okay? And so we've got grams to moles right here, this step. Okay? And then this is moles to moles, or mole ratio, okay, which we got from our equation up here. Excuse me, from our equation up here once we balanced it. And then moles back to grams. Okay, grams to moles, moles to moles, moles to grams. Okay. And then everything else is just following the same rules. You got to have units that are consistent. You can't just magically change from grams to milligrams. So this spit out grams, so I went ahead and made that conversion. And you can see how I would, if I had added that down there, it would have been kind of out of space. So I wish I could have shown that. Sorry. All right. But at the end of the day, you multiply, then you divide, and that's your answer. There really should only be one time you ever punch anything into a calculator. Grams to moles, moles to moles, moles to grams. And just read your question carefully. Sometimes you'll be given moles and end up in grams, which means you've only got to do this step and this step. Sometimes you're given grams and you're going to go to moles, so you only got to do this step and this step. Sometimes you got to do grams to grams, so this. Okay, you just need to read. So you're doing this, you're doing this, you're doing the whole thing. It's always the same order, and it's always this same conversion pattern here, okay? And it all comes from a balanced equation right there, okay? You guys have some time. I'm going to send one or two to work by Miss Barron, but they all work the same way, okay? And anytime I give you these, I'm going to give you probably the unbalanced equation. You balance the equation, you set up your problem, you do the math, you get the answer, that's it. Okay, so stoichiometry, there's nothing super complicated about it, especially if you think about it as a conversion problem. Okay, very quickly, let's talk about what's going to be on your quiz and what's not going to be on your quiz. Okay, so remember we pushed this back because I wasn't real comfortable with it. Okay, so let's talk through what types of things. So we're covering 7.1 and 7.2. Okay, so maybe from this section I might ask you something like, is chemistry interesting? And the answer is yes. Or perhaps, no, it's not just interesting, it's fascinating. Okay, of course I'm just kidding there. You need to know some of these vocab. Miss Forster says that I'm funny, in case you didn't hear that. It's recorded, so everyone knows now. All right, so make sure you know these vocabulary here. Just read through some of this. Law of conservation of mass. That's what number 9 was that we talked about a little bit ago. That's an important concept. All right, reaction notation. If I give you the words, you need to be able to write them in a way that is proper. Okay, you need to know what that delta means there. You need to know what solid, liquid, and gas are represented by. That's that. You need to be able to balance equations. We've done homework on that. And if you have any questions, let me know. Okay, you need to be familiar with this right here. You need to know 7 of these are diatomic. And again, they're just these guys. N2O2F ClBrI and then hydrogen. Okay, so take a look at those. Those are things that you're going to have to just know. Okay, no one's going to remind you, hey, remember that H is always H2. All right, so balancing equations is going to be a large part of it. Doing oxidation states is going to be a large part of it, and telling whether something has been oxidized or reduced. Okay, I'm sending you a video that I want you guys to watch on oxidation and reduction. He does a better job explaining it than I could do unless I just kind of copied what he said. And we don't have time for that today. So watch that. It's 15 minutes. Very clear. You can fast forward it if he gets a little slow for you. But you need to know what it means for something to be an oxidizing agent and what it means for something to be oxidized. Those are opposite. Okay? And oil rig, oxidation is loss of electrons, while reduction is gain of electrons. Okay? And if something is reduced, the only way it is reduced is by oxidizing something else. Okay, so he goes into all that. So you'll need to know that. You'll need to be able to find an oxidation state, and you'll need to be able to calculate whether something is being oxidized or reduced, and tell me that. Okay. You need to know the general types of reactions. Excuse me, I'm off the camera here. Synthesis, decomposition, single and double replacement. Okay. And then combustion and acid-base neutralization. All right. And then you need to know what this means. Okay. There will be a question or two about, will this reaction go? Okay. And the answer is, if the metal in the compound is lower than the free metal that's like out in solution or whatever, then yes, it will go, because this guy comes in there and he boots the other guy out of that compound, okay, and takes his place. But if it's the opposite, just nothing happens, okay, because the higher activity metal is already bound up with another compound or another ion, okay, and the lower activity metal is not strong enough to wrest that ion away. All right, so but that's just essentially, it'll be a yes, no, with and explain why, and that explanation will be because zinc is lower on the activity chart than lithium, okay, and you will have that chart on the quiz. Okay, all right. What we've covered today will not be on there. Stochiometry is not on there. Okay, that will just be on the test, and we'll have plenty more time to work on all of that. Okay, so don't fret about that. Go back and look. Make sure you can work all the things from 7.1 and 7.2. We're not going to have a lot about redox reactions as a whole topic, okay? Because we have a whole chapter on that later, and we're not gonna really focus in on that. Other than I may say, hey, label the oxidation states. Tell me what's oxidized. Tell me what's reduced. Okay, and that will be that. Okay, all right. I've talked long enough. I will talk to you all soon. Thank you.